Hello students, welcome to EPG Patashala. I am Professor Gaurinath from School of Life Sciences, Jawaharlal Nehru University. Today we are going to talk about module on bonds in proteins and peptides under the paper Biomolecules and Their Interactions. So as this is the first module of this paper, so here basically we are going to learn about different chemical bonds that are present in proteins and how these are different, how these contribute to protein structure. We will learn about it. So here we will learn about physiochemical properties of different chemical bonds, so like covalent bond, coordinate covalent bond, metal coordinated bonds, ionic bonds, hydrogen bond, Vander Waals interaction, or we also call them as hydrophobic interactions. The bonds in proteins and peptides basically is all in chemistry. You might have learned this in your high school. Basically, they link atoms each other through bonds, which are resulting formation of a strong attractive force that exists between two atoms. Bonds form when electrons from different atoms interact and share with each other. Now, these are generally valence electrons found in atoms' outermost shell, and where these electrons could be shared between these two atoms. There are of course different bonds. Not all the time you have sharing of electrons. The strength of the bond, which depends on what kind of bonds it is forming. Like if it is a strong bond or a primary bond, which is a covalent bond, or metallic bond, which are generally relatively very strong, and they do not have large variation, or you cannot break them easily. And you have weak bonds or secondary bonds, which are like hydrogen bonds, ionic bonds, Vander Waals interaction, or hydrophobic interactions, which are generally weaker than the ionic bond, covalent bonds and metallic bonds. Now we'll come one by one, all the bonds we will discuss here with detailed physiochemical properties. The covalent bond is the first one, which is most common. You have learned most of in your schools and colleges, is basically where the two atoms contribute one electron each, and they are shared between these two atoms. And these are, again, you have different bonds here. The sigma covalent bond is the most common, which is a single bond, very flexible, and the planarity depends on the type of atoms it connects. The polarity depends on the type of atoms it connects. If the bonding two atoms of equal electronegativity, it will be non-polar covalent bonds. So a typical example is carbon-carbon bond, where the two electrons are shared equally between the two carbon atoms. If the bond is between the highly electronegative atom and a less electronegative atom, then it actually leads to charged covalent bond or polar covalent bond. Example, OH or HCl. The covalent bonds which connect two atoms, they are kind of rigid, but after all, they are electrons shared by two atoms. So the cloud of electrons is flexible. If it is a single bond, the two atoms can rotate on single bond. So a simple example is ethane. So ethane, you can have a staggered conformation or eclipse conformation, and the energy between them, difference between them, is about 2.9 kilocal per mole. So in the staggered conformation, the hydrogens of the two different carbons are about 60 degrees far away from each other, and when they rotate about 60 degrees on the single bond, the hydrogen atoms come closer, and that becomes energetically less favorable. So you can look in the energy plot of this rotation. So every 60 degrees you have higher energy state and the lower energy state. Basically, the three hydrogens, you have 360 degrees divided by 3 is about 120 degrees, and every 120 degrees you have maxima, and every 120 you have a minima. So that means every 60 degrees you have an energy maxima and an energy minima. Now here these three hydrogens are a same atom, so the energy maxima and minima will be the same. Suppose if you have a different atoms on these carbons, then the energy plot will be completely different. Now if you look at the left side of the slide, you have an energy diagram of butane. In this you have 4 carbons, and suppose if you are rotating on the carbon 2 and carbon 3 on the single bond. So there is 2 methane groups on the second carbon and the third carbon. So whenever these methanes come closer, so within the stagger you have 2 different energy states. One, the methanes are exactly opposite to each other, that is the lowest energy state, and other staggered state where methane is closer to other methane but not exactly in eclipsed conformation. So that is also you have energy differences. Now if you imagine, if you convert this, think about this in the case of proteins. You know, the single bond rotations are 5 psi. We will discuss further in other modules, but the single bonds are 5 psi. Like the 5, we have 3 different groups of C alpha and N, or in the case of psi you have 3 different groups on carbon, and other is a CO with a peptide bond, and that is a planar. Now imagine how complex the rotation energy diagram on these bonds. The planar group rotating on 5 psi, the dihedral angles, are interdependent and results in more complex energy diagram. Dihedral angle. Dihedral angle is basically the rotation on the single bond if the atoms are rotated, and which is explained by dihedral angle. Now when you say that rotation on a single bond becomes very difficult to understand. So for classical simple examples, I have shown here, if you have 4 atoms connected by each other, let's say you have one atom here, one atom here, one atom here, and another atom here, and if this is the bond which is rotating, and so this is how you can easily visualize here, right? So there's a plane forming between A, B, C, that's one plane, and the plane forming between the B, C, D, the 2 planes. So the angle between these 2 planes is basically, you can explain the dihedral angle. Typically the cis conformation where these 2 planes are in plane, so the angle between these 2 planes is 0. And if you rotate like this, it's in the clockwise direction where the angle is 90 degrees. And if it is a trans conformation, this is the angle between 2 planes is 180. So if you go in anti-clockwise, this becomes minus 90, and if you go down, that becomes minus 180. Here you can see in the picture where I have shown you those in the picture clearly, the ABCD, and there's 2 planes forming between ABC and BCD, and that's how you can measure the angle. And this is how it is measured in the protein structure. So as we discussed before, the potential energy on simple ethane and butane, we have seen the energy potential, which is very simpler. But in the case of proteins, the energy potential is little more complex, as I described before. Here you can see it in this equation, energy potential due to the dihedral angle, you can see here. So the V is the potential energy, energy barrier for the rotation. N is the number of maxima. So if you have 3 different atoms on one carbon, so you will have 3 energy maxima. And if you have 2 heavy groups, so you will have 2 energy maxima, if it's a double bond kind of a thing. And one is a gamma, is a angular offshoot. So in the case of 5 psi, in one side you have 3 groups attached, and another side you have only 2 groups attached. So it could be N is from 1 to 3, and this is how you can calculate the energy potential for the dihedral angle in proteins. So what are the conformations? Different molecular structures form due to rotation on these single bonds. So the groups which rotate on these single bonds causes different structural states. So these structures, which we call a conformer, and these are different states which we call them as conformations. Now the analysis of energy differences resulting due to this rotation of single bond is what we call as a conformational analysis. So several times the protein structures do change their structure just because a rotation on the single bonds, and you have different conformations that could lead to small changes in the function and sometimes more. Now the next one is the bond length. The bond length is not constant because the bonding orbitals can expand or compress, and it behaves just like a spring. As I said before, it's basically the two atoms which share electrons, and these electron cloud is very flexible, so they could be expanded or compressed depending on the necessity in the structural requirement. So the energy potential difference for the bond in a molecule is generally explained by Hooke's law. So you can calculate the energy potential due to the change in the bond length by Hooke's law. So you can see the diagram here. The energy minima, which we generally call as a bond length, like example, carbon-carbon, we call it as a 1.54 angstrom for the single bond. But, so this at the room temperature, let's say you have, as indicated, there's enough energy that this carbon-carbon movement can have. You can have a change in the distance between these two carbons. The bond length can be changed, and our body temperature, let's say, it's 37 degrees. So we have still further higher energy state. So the molecule can actually vibrate like a spring. It can expand and compress. So here the R is the bond length, and R is a bond length at equilibrium, that is lowest energy state of the bond length, and K is a spring constant, which varies from bond type to bond type. Like carbon-carbon it is different, and carbon-nitrogen it is different. So with this you can calculate the energy potential due to the change in the bond length. Polar covalent bond. So far what we have seen is where electrons are donated by two atoms and shared by two atoms. But in the case of polar covalent bonds, they are similar to covalent bonds where electrons are contributed by both atoms, but these electrons are majorly shared by one atom, and that becomes electronegative atom, and the one which gives the electron becomes electropositive atom, and these basically they almost become a positive charge and negative charge. And these are also discussed in the ionic bonds. These actually results in ionic bonds where you have a one lead to a positive charge atom and another leads to a negative charged atom. Example, you have all these ionic salts, acids, bases. Like example, in the acids you have sodium hydrochloric acid, in the bases you have sodium hydroxide, or salts like sodium chloride, which are low, they are more like a polar covalent bonds, or you can call them as ionic bonds. So in proteins, the acidic basic amino acids which do form polar covalent bonds, we will discuss them as a ionic bonds or salt bridges later. So the covalent bonds could be pi bonds. So the first bond which generally formed between the two atoms, we call them a sigma bond. And if you have lone pair of electrons which still there with the atoms, and they form a pi bond, basically the p orbitals share, and these called a pi bond. And a pi bonds results from overlap of orbitals, and they are more diffused bond compared to a sharper sigma bonds. Now, when the pi bond is formed, molecules cannot rotate on pi bonds. So the typical example is ethylene, the carbon-carbon double bond. And so you have a one double bond consists of a sigma bond and a pi bond. So here, when you have a double bond, so you call them as a cis and trans conformation, and generally they are not interconvertible. Now, if you have a double bond, CC double bond, which is always less than the CC single bond. And if you have a triple bond, that bond length will be much smaller than the double bond and the single bond. Pi bond decreases the bond length between the atoms. So the pi bond, where electrons you have in the proteins, the CO which forms a pi bond. And just besides that, the nitrogen, which has a lone pair of electrons, and these lone pair of electrons from the nitrogen and the carbonyl group, the CO group, which the lone pair of electrons from there, they can actually delocalize between the nitrogen and oxygen. And because of that, the peptide group, which will have a planar group, is a partially double bond group. So the rotation on the peptide bond is energetically very less favorable. It almost behaves like a double bond. So the rotation is generally not possible, and moreover, here the cis conformation is energetically less favorable and trans is always more favorable. That's why proteins generally prefer trans conformation, and most of our calculation and considerations, we generally keep peptide bond as our only trans conformation, and we never consider existence of cis bond. But there are cases like proline, we can have a cis and trans proline. That is very rare. Other amino acids, this conformation is very rare. So delocalization of electrons and pi bonds is very common. You might have learned from your high schools that, like, a simple example is benzene, where you have a 3 double bonds alternatively, but actually speaking, these could be in equilibrium. So the double bond could be exchanged between the carbons, and eventually what we call them as delocalized double bond. And when you have delocalized double bonds, the structures become planar. So in proteins, we have 3 ring structures, phenylalanine, tyrosine, and the indole group of tryptophan, where there are several double bonds, and because of that, the electron delocalization happens. So these ring structures are very planar. So even though there are several single bonds, because of the delocalization of electrons, these ring structures cannot change, and they have to be in planar conformation. The bond length and bond angle depends on the hybridization of bonding atoms and the number of bonds formed between these atoms. Like you have sp3 hybridization of carbon, you will have different bond angle. If you sp2 hybridization, you have a different bond angle. Similar to bond length and bond angle is also not constant. It behaves like a spring. So this is basically the electron crowd. If there is an angle, it could actually fluctuate. So the potential energy of the bond angle is also explained by Hooke's law. So you can have energy potential due to angle is basically Hooke's constant, the difference between the bond angle, that is the band angle, and the equilibrium bond angle, that is the lowest energy state, and K is the spring constant, which varies from the type of the bonds which is formed between the 3 atoms. You can see here the energy potential plot for the simple bond angle. So you have an energy minima where the lowest energy state, where that is a equilibrium angle, and you can have a fluctuation in the bond angle, and that's where you have the room temperature level, which I have showed you in the plot. So if you have again, as our body temperature is more than the room temperature, so you can have literally much more fluctuation in the bond angle. So here you can I showed you the example of ethane, ethylene, and acetylene, where you have a different hybridization of carbon, and the both bond length and bond angle varies between these carbon hydrogen atoms. So the next bond is coordinate covalent bond. In the covalent bond, what we have learned is that each electron is contributed by 2 atoms. The pair of electrons is shared by 2 of them. But in the coordinate covalent bond, only one atom gives 2 electrons, and then the electrons are shared by the 2 atoms. So the classical example in your schools, you might have learned the bond between ammonia and boron trifluoride. So the ammonia, which has a lone pair of electrons, and boron trifluoride, where it lacks 2 lone pair of electrons in the outermost orbit. So then this ammonia can give these 2 electrons, and these both ammonia and boron trifluoride can actually share those 2 electrons, and this is actually the coordinate covalent bond. So the ammonia, which acts like base, and boron trifluoride here acts like a mild acid, and so it accepts the lone pair of electrons from the nitrogen, and they both share. In proteins, the coordinate covalent bonds are generally seen in the metal coordinated bonds. So the coordinate covalent bond with a metal and oxygen of water, or aspartic acid, glutamic acid, nitrogen of ammonia, or in the proteins you have imidazole, and sulfur of cysteine are the most common. So here I have shown you example of cobalt chloride. Ammonite hexachloride is where cobalt 3 plus accepts the lone pair of electrons from 6 ammonia molecules. So these kind of metal coordinated bonds are very common in proteins. Almost 1/3 of proteins are metalloproteins. In proteins, the metal ions are coordinated by, as I said before, nitrogen, oxygen, sulfur belonging to amino acid side chains, nitrogen from imidazole group of histidine, sulfur from cysteine, and oxygen from carboxylate groups of aspartic acid or glutamic acid, which are predominantly seen in proteins. The backbone nitrogen carbonyl oxygens were also seen in metal coordination in several proteins. So I will list out several examples of metal coordinated proteins. So example, you have a zinc coordination. Zinc atom can form different coordinate bonds and perform different functions in proteins. First example is a structure stabilization. That is a zinc finger motif. The zinc atom coordinates between the 2 nitrogens from 2 histidine side chains and 2 sulfur from the cysteines and stabilizes the fold to form a tetragonal conformation. And so the small 2 beta strands which form a beta sheet and a small helix, this motif is stabilized by the zinc atom. Otherwise these structures cannot stay together. And zinc atoms are also seen in several transcriptional factors forming zinc clusters. So you can further details we can see in the module 9. Zinc is also seen in catalytic sites. Example is carbonic anhydrolase, which I have showed you the catalytic site here, where zinc coordinates with the 3 histidines and the 4th one is water, which is flexible. So here the water can be moved out and that forms the active site. So here the interconversion of carbon dioxide and water to bicarbonate and protons occurs. And this is a reversible reaction. That's how the metals also participate in the catalytic activity. So another example is calcium coordination. So calcium is used in proteins in both as structurally and signaling. And signaling is very crucial function of the calcium. Calcium binding proteins which has a signal properties generally have E-affine motif which senses the calcium concentration and binds to calcium, and upon binding calcium the protein changes its conformation and binds to other functional proteins to regulate their function. So further details you can see in module 9. You can see the coordination, how the calcium coordinates in the figure. So it basically forms pentagonal bipyramidal structure. So the pentagonal coordination and one side of the pyramidal coordination comes from the protein and the other coordination comes from the water. So there are also several storage protein which store the calcium in the cell, and they are structural protein which bind to a calcium in very similar coordination, but their structural changes do not happen. Another example of metal coordination is iron. Iron forms tetragonal bipyramidal coordination. It's seen in several important biological molecules performing several functions such as oxygen carriers, which we all know, hemoglobin, and you also see iron in oxidation reduction reactions and catalysis. Hemoglobin is the oxygen transporter and it consists of a heme group which I've shown you in the right side figure. So the iron is coordinated by heme group 4 nitrogens and there is a histidine below the plane of the heme group, and where with ammonia with nitrogen lone pair of electrons it coordinates, and there is the oxygen which binds on the top. So that's where the oxygen or carbon dioxide can be coordinated with iron. We also have cytochrome kind of proteins where heme group is there in the active site which performs oxidation and reduction reactions, and you can also see the examples in catalase enzymes contains porphyrin groups coordinating with iron, which catalyzes the conversion of hydrogen peroxide to water and oxygen. Copper can also form multiple coordination numbers. The example I have showed right side, one is a octahedral or tetrahedral, where it can form 6 coordination, and it can also have 4 coordination. But in the lowest case, it can also form 2 coordination. So example, you can see in plastocyanin, a copper binding protein involved in electron transfer reactions. That's a figure you can see. It coordinates with 2 cysteines, 2 histidines. And copper binding site is seen as a trigonal pyramidal geometry with 4 coordination. So with the 4 coordination, it exactly doesn't form tetrahedral geometry, but a little modified version of geometry which is seen in this protein. We'll see a couple of more examples of metal coordination. The one which is classical example is S4D enzyme, which catalyzes the superoxide, the O2 minus radical, to form a normal oxygen or hydrogen peroxide. Interestingly, S4D can bind to copper, manganese, iron, nickel at the active site for this reaction. So different S4Ds have different metal coordination. The right side, which I've showed you the figure, that's the active site of human S4D, which binds to the manganese. So the manganese coordinates with 3 histidines, and the fourth side is open for the reaction. So here you can see how the manganese converts the superoxide to oxygen and hydrogen peroxide. So this is how the manganese bound S4D can function. So there are several catalyzers as I said. Here the one example is the copper zinc coordinated S4D. These are generally a prokaryote S4D. They are also present in human S4D, in the human cytosol. So here copper 2 ion participates in the square bipyramidal coordination with 4 histidines, and basically the copper is the active site, and binding of O2 minus the superoxide results in copper plus the electron transfer, and that results in oxygen release. At this state, the protonated histidine binds to only the zinc atom. So you can see the whole reaction down below, and this is how copper and zinc cluster together function in converting superoxide radical to normal oxygen and H2O2. Ionic bonds, which is another weak interaction you can also see in the proteins. They are generally electrostatic attraction between oppositely charged ions. The ions that gain 1 or more electrons are called anions, which are negatively charged. The atoms give 1 or more electrons are called cations, which are positively charged, which we have learned in all our textbooks from the school time. But this transfer of electrons is called electrovalence. In simplest cases, cations are the metal atoms and anions are the halogens, or non-metal electronegative atoms, or ions of complex nature. In simple words, ions are formed by transfer of electrons from a metal to a non-metal to obtain a full valence shell for both atoms. These two charged atoms come together to form ionic bond. The simple example is sodium chloride. Here we know sodium has 11 electrons, so it can easily give away 1 electron and have a satisfied outermost shell, and chloride you have 1 less to fill the outermost shell, so it can take 1 electron. So sodium ion will become positive and chloride ion become negative charged. The ionic bond is it's basically extension of covalent bonding, that is electron sharing, but this is generally happen due to a polar covalent bonds. Here the electronegativity difference between these two atoms is very high. Therefore, the bonds become more ionic than covalent. The ionic compounds conduct electricity in solution, as ions can be separated from each other, and these ions are easily soluble in water. They can carry electricity. The ionic compounds are generally a solid and have very high melting point. They follow maximum packing rules. They generally have high coordination numbers. Example, you have a sodium chloride here where each ion forms 6 bonds and all bonds are about 90 degrees, which you have learned in your school textbooks, how the sodium chloride crystal is arrangement is, you can see that. And this attractive force between these two atoms follow a simple Coulomb's law. Here you can detail, you can also see in module 3. In proteins, the ionic bonds are called electrostatic interactions or salt bridges, and they are generally formed between the carboxyl groups of aspartic acid, glutamic acid, which are negatively charged, and the guanidinium group of arginine or amino group of lysine, which are generally positively charged. So these negatively charged and positive charged can attract each other and form salt bridges or ionic bonds. And also the amino terminal and carboxy terminal, which will also form ionic interactions. So here a simple example, you have a positive charge, negatively charged, how the Coulomb's law functions, the equation you can see that. Hydrogen bond. Now, hydrogen bond is kind of electrostatic attraction between two pair of groups when hydrogen atom is covalently bound to a highly electronegative atom comes in between these two polar groups. Generally, both polar groups are electronegative atoms such as oxygen, fluoride, nitrogen, etc. These are generally weaker than the covalent and ionic bonds, and classical example is the water, the hydrogen bonds in water. So which the hydrogen bonds are responsible for high boiling point of water compared to the same group hydrides, generally described as XH, that's a hydrogen is connected to X atom, and the Y, the dot dot which showed, is actually hydrogen bond, where both X and Y are electronegative atoms. So the hydrogen covalently bound to a relatively electronegative atom will play as hydrogen bond donor. So what happens? The electronegative atom tries to pull the electrons towards itself, and then partially the hydrogen atom becomes partially positive charge. So other electronegative atom which has lone pair of electrons to the hydrogen positive charge atom which try to attract the lone pair of electrons. So the electronegative atoms pulls the electron towards itself. The hydrogen atom becomes partially positive charge and tries to attract lone pair of electrons of other electronegative atom. And generally what we see in proteins is NHN hydrogen bond or OHN hydrogen bond. These are the two typical hydrogen bonds which we see in protein structures. These hydrogen bonds are often described as a dipole-dipole interaction, but it also has several covalent bond characters, like it's directional. So the hydrogen and the lone pair of electrons of the other atom should be in the same plane. Then only the hydrogen bond strength is larger. If the atoms are perpendicular, the hydrogen bond is the weakest. The hydrogen bond distance is smaller than the sum of two van der Waals radii. This has a limited parameters, like it is basically decided by valence of those electronegative atoms. And these are the weak electrostatic interaction with the directional property, as I said just before. In proteins, we have hydrogen bond NH4, that is a more common, which is responsible for secondary structure characterization, like helix or beta sheets. The hydrogen bond distance varies from 2.7 to 3.5 angstroms, which is on an average we generally can also say it's about 3 angstroms. You can also see more details of hydrogen bond in protein structure in module 3. The other bond or other interaction in the proteins is van der Waals interactions. These are a distance dependent interaction. There is no chemical electronic bond between the atoms. These are very weak bond compared to all other bonds discussed or studied so far. These are result of both attractive and repulsive forces acting on two atoms or molecules. These forces develop due to transient shift of electrons, which develop transient charge on these atoms, and those transient charges can attract or repulse. Van der Waals interactions is another weak, very transient bond which is seen between general atoms, any atom. This is caused because of transient shift of electrons that can lead to a formation of a dipole or multipoles. The intermolecular interactions have four major forces. So one is dispersion, which is also explained by London dispersion force, which you have, again, these are very basic, which you have learned in chemistry. Here we are extrapolating to the protein structures, which resulting multipoles. The induction or the polarization, where one molecule can induce polarization in other molecules. Like example, if your two atoms come close together, there is an electron cloud of one atom can be attracted towards the nucleus of other atom, or the attractive or repulsive interactions in these multipoles or induced poles. Induced poles can have both attractive as well as a repulsive forces, and the dominant repulsive force between these electron clouds or nucleus, when these two atoms comes much more closer, then the electron cloud and the nucleus can repel, and this is more dominant when the atoms come very close. This kind of interaction common in hydrophobic interactions, where you have a carbon-carbon kind of a thing. This kind of interaction is very common. The attractive and repulsive forces are generally described by Lennard-Jones potential. This is thermodynamically very favorable phenomenon. It's entropy driven. Van der Waals interactions are one of the most important interactions for protein stability and protein folding. Here you can see this in the energy potential plot, where in the two atoms the R is far away, the energy, there's a small attractive force, but when they come closer, the attractive force increases and that reaches the energy minima. And if the atoms come much closer, and suddenly the repulsive force become dominant, and then they repel, and that becomes dominant when the atoms becomes too close. The attractive interaction is long range than the repulsive. When the two atoms are far away, there is more attractive term is dominating, but once the distance becomes short, the repulsive interaction becomes dominant. The electron cloud of two atoms and the nucleus of two atoms repel each other. This results a minimum energy state where two atoms are positioned at optimum distance. So generally the Van der Waals potential is described as Lennard-Jones equation 6 to 12 potential function. So the energy potential is described by Lennard-Jones equation. Here you can see that the R is basically the distance between the two atoms, and A, B are constants. They are depending on the type of amino atoms involved in these interactions. So students, let's now summarize what we have learned in this module. We have learned about different bonds and interactions involved in proteins. This knowledge of bonds gives us understanding of the flexibility and the rigidity of protein structure. The summation of all these potentials is due to all bonds gives us the total empirical energy. Now this function is distinguishable with respect to atomic coordinates. This gives us the direction of protein folding, which is generally used in molecular dynamics. You can also see little more details of this one in the module 3, where this old total energy of potential, how it is used. So now with this overall learning from flexibility of atomic bonds, we can understand how the protein is flexible and how it must be breathing, because you know the bond angles, bond lengths, everything is flexible. Thank you.